Hello students, in the last class we learnt about the classification and the nomenclature of haloalkanes and haloarenes. In this class let us learn about the preparation of haloalkanes and haloarenes. Let us discuss one by one. That is, first one, preparation of haloalkanes. Here there are different methods to be used to prepare the haloalkanes, in which the first method is preparation of haloalkanes from the alcohols. That is, alcohols are to be converted into alkyl halides. Alcohols are represented by the general formula ROH. So the haloalkanes are represented by the general formula RX. That is, from the alcohols, OH is to be replaced by the halogen. So this conversion is to be called as preparation of haloalkanes from the alcohols. Here there are different reagents are to be used to replace the hydroxyl group from the alcohols. Let us learn one by one. That is, first one, by using hydrogen chloride. This method is to be called as Gauss process. That is, alcohols reacts with the hydrogen chloride, that is concentrated HCl, and the reaction takes place in the presence of anhydrous ZnCl2, anhydrous zinc chloride. Here there is an elimination of OH group by the Cl. Elimination of OH group or replacement of hydroxyl group by the Cl. So it gives the product, that is RCl, and the remaining, that is hydrogen from the HCl, combines with the hydroxyl group of the alcohol. It gives water molecules. That is, alcohols to be converted into haloalkane. Haloalkane, that is ROH and HCl. OH and hydrogen combined, it gives the water molecules, and R combines with the Cl, it gives RCl. Let us take an example, that is methanol. That is conversion of methanol to methyl chloride. Methyl chloride. That is, we have to convert this methanol to methyl chloride. So methanol is represented as CH3OH, and this methanol is treated with the concentrated hydrochloric acid in the presence of anhydrous ZnCl2, anhydrous zinc chloride. So this anhydrous zinc chloride acts as a catalyst, that is, it increases rate of chemical reaction, and it gives the product, that is OH and hydrogen is to be eliminated as water molecules, H2O, and the main product is CH3Cl. That is conversion of methanol to methyl chloride. And let us take one more example, that is conversion of ethanol to ethyl chloride. Ethyl chloride. That is, ethanol is to be represented as C2H5OH, and this ethanol is to be treated with the hydrochloric acid in the presence of anhydrous ZnCl2. So it gives the product C2H5Cl and water molecule, that is H2O. That is, when the ethanol reacts with the concentrated hydrochloric acid in the presence of anhydrous zinc chloride, it gives ethyl chloride, or it is to be called as chloroethane. Here the mixture of concentrated hydrochloric acid and anhydrous ZnCl2 is to be called as Lucas reagent. Lucas reagent. Very, very important for 1 mark. That is, they may ask in the examination, what is Lucas reagent? So Lucas reagent is a mixture of concentrated hydrochloric acid and anhydrous zinc chloride. And let us take one more example, that is preparation of haloalkenes from the alcohol by using sodium bromide. That is, when alcohol, that is ROH, reacts with the sodium bromide NaBr in the presence of sulfuric acid. Here sulfuric acid acts as a dehydrating agent. The simple method to remember the byproducts of the chemical reaction, that is sodium bromide on ionization it gives Na plus and Br minus, and H2SO4 on partial ionization it gives H plus and HSO4 minus. That is, positive part of the NaBr combines with the negative part of the sulfuric acid, so it gives one byproduct, that is NaHSO4, sodium bisulfate. And from the alcohol, that is OH combines with the H plus, because OH has negative charge, alkyl group has positive charge. That is, OH combines with the H plus, it gives H2, water molecule. And the remaining, that is R combines with the Br, it gives the haloalkanes. So this is the simple method to remember the what are the products to be obtained when the alcohol to be reacts with the sodium bromide in the presence of sulfuric acid. That is, when alcohols reacts with the sodium bromide in the presence of an acid, it gives bromoalkane. For example, let's take methyl alcohol, that is CH3OH. When methanol reacts with the sodium bromide in the presence of sulfuric acid H2SO4, so it gives the product, that is the main product, that is R. Here R is CH3 and halogen is Br, plus sodium combines with the negative part of the sulfuric acid, that is NaHSO4 plus H2O. That is methanol to be converted into methyl bromide, or it is also to be called as bromomethane. So methyl bromide is the common name of CH3Br, and bromomethane is the IUPAC name of the CH3Br. And let us take one more example, that is ethanol. It is to be represented as C2H5OH. So when the ethanol reacts with the sodium bromide in the presence of sulfuric acid H2SO4, so it gives the product, that is C2H5 and Br plus NaHH4 plus H2O. That is ethanol to be converted into ethyl bromide. That is the preparation of alkyl halides by using sodium bromide. Next method of preparation of haloalkanes from the alcohol by using red phosphorus and halogen gas. That is, when alcohols reacts with the halogen gas in the presence of red phosphorus, so it gives the product that is Rx. For example, let us take methanol CH3OH, that is methanol reacts with bromine gas in the presence of red phosphorus, so it gives CH3Br, so it is bromomethane. Or let us take one more example, that is ethanol C2H5OH, that is ethanol reacts with iodine gas in the presence of red phosphorus, it gives the product that is C2H5 and it is I. It is to be called as iodomethane. And let us take one more method to prepare the alkyl halide from the alcohol by using phosphorus trihalides. That is, ROH reacts with the phosphorus trihalides, that is, it contains 3 halogens, px3. It gives the product that is OH and phosphorus to be eliminated as a byproduct, and because of the presence of 3 halogens, the alcohol is to be taken as 3 moles, that is, it gives 3 moles of Rx, that is R combines with the halogen, plus the byproduct is to be represented as 3 hydrogens or H3 and 3 oxygen atoms and 1 phosphorus, that is H3PO3. That is, whenever the organic compounds or reacts with the phosphorus trihalides, the obtained byproduct is H3PO3, that is phosphorus acid. For example, let us take methanol. So methanol to be converted into methyl bromide, that is CH3OH reacts with the PBr3 phosphorus tribromide, so the eliminated products are H3PO3 and the main product is CH3Br, and it is 3 moles and it is 3 moles. Next example, that is conversion of ethanol to ethyl iodide, that is ethanol C2H5OH. When the ethanol reacts with the phosphorus triiodides, so it gives the product that is C2H5 and it is I plus H3PO3. That is, when the alcohols reacts with the phosphorus trihalides, the obtained product is haloalkanes and the byproduct is always H3PO3. And next, preparation of alkyl halide from the alcohol by using phosphorus pentahalides. Phosphorus pentahalides means it contains 5 halogen atoms. Here X is either Br or iodine or Cl. Let us take alcohol, that is ROH, reacts with the phosphorus pentahalides, and the products are to be represented as, that is, by using the simple method we can predict the what are the products are to be obtained when the alcohols reacts with the px5. That is, px5 is to be represented as X, and it is px3 and it is X, and alcohols to be written as ROH, that is POX3 is one of the byproduct and HX is another byproduct, and the main product is RX, that is RX plus POX3 plus HX, that is when the alcohols reacts with phosphorus pentahalides, it gives alkyl halides. Alkyl halides. For example, let us take methanol. So when the methanol reacts with the phosphorus pentachloride, and the obtained products are to be represented as, that is CH3Cl. So the same method to be used to write the byproducts, plus of px3, here X is Cl, so it is POCl3, and the next byproduct is HCl. That is when the methanol reacts with phosphorus pentachloride, it gives methyl chloride. And let us take one more example, that is ethanol, C2H5OH, ethanol. So when ethanol reacts with the phosphorus pentabromide, it gives the product, that is C2H5Br plus POBr3 plus HBr, that is conversion of ethanol to bromoethane. Next method, preparation of alkyl halides from the alcohol by using thionyl chloride. So this method generally to be called as Darjan's process. Thionyl chloride. So the formula for the thionyl chloride is SOCl2. That is when ROH alcohols reacts with the SOCl2 in the presence of pyridine. So the reaction takes place in the presence of pyridine, and the byproducts are represented as, that is the simple method to remember the byproducts obtained when alcohols reacts with the thionyl chloride, that is ROH, and SOCl2 is to be written as Cl, Cl and SO. That is the products are main product, that is RCl plus SO2 plus HCl. That is when the alcohols reacts with the thionyl chloride in the presence of pyridine, it gives haloalkene. Let us take an example, that is methanol to methyl chloride in the presence of thionyl chloride. That is methanol, that is CH3OH reacts with the thionyl chloride SOCl2 in the presence of pyridine. So it gives the product, that is CH3Cl, like RCl, plus the byproduct is SO2 gas, and another byproduct is HCl. And let us take one more example, that is conversion of ethanol to ethyl chloride. That is, ethanol is to be represented as C2H5OH. Ethanol to be reacts with the SOCl2 in the presence of pyridine. So it gives the product, that is C2H5Cl plus SO2 gas plus HCl. That is conversion of alcohol into alkyl halides by using thionyl chloride. Here, pyridine being basic in nature, and it removes the HCl formed during the reaction, hence it increases the rate of reaction, and this is the best method for the conversion of alcohol into an alkyl halide, because the obtained byproducts are in the gaseous state, and this method cannot be applied for the preparation of alkyl bromide and alkyl iodide, since SOBr2 is unstable. That is, SOBr2 is unstable, it is not stable, and SOI2 does not exist. That is, this method is only used to prepare the alkyl chloride, but not the alkyl bromides or alkyl iodides. And this method not to be used for the preparation of aryl halides. That is, aryl halides means that is C6H5 and it is X, because the carbon oxygen bond in the phenol has partial double bond character. That is, in the aryl halides, so the bond between the oxygen and carbon has partial double bond character. In order to break this bond, it requires more energy. Hence, this method is generally not used for the preparation of aryl halides. Let us see the flow chart of the preparation of haloalkanes from alcohols. So first method, that is HX in the presence of anhydrous ZnCl2. So it gives the product RX plus H2O. And the next method, that is reaction with the sodium bromide in the presence of H2SO4. So it gives the product, that is RBr plus NaHSO4 plus H2O. And the next method, that is reaction of alcohol in the presence of halogen gas in the presence of red phosphorus. So it gives the product RX. And the next method, reaction of alcohols in the presence of PX3 in the presence of phosphorus trihalides, it gives the product, that is RX plus the byproduct is H3PO3, phosphorus acid. And in the presence of PX5, so the product is RX plus POX3 plus HX. And the reaction of alcohols with the thionyl chloride SOCl2, so it gives the product, that is RCl plus SO2 gas plus H2O. So these are the 6 methods used to convert alcohol into alkyl halides, in which the best method is the conversion of alcohol to alkyl halide by using thionyl chloride. Next method, let us study how can we get alkyl halides from hydrocarbons. That is, the free radical chlorination or bromination of alkanes gives a complex mixture of isomeric mono and polyhaloalkanes, which is generally difficult to separate as a pure compound. For example, let us take butane, CH3, CH2, CH2, CH3. So when the butane undergoes chlorination in the presence of sunlight, or chemical reaction takes place on heating, it gives isomers, that is CH3, CH2, 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 Cl, and another isomer is CH3, CH2, CH, and it is Cl, and it is CH3. That is halogen attached to the first carbon, and here halogen attached to the second carbon. Hence the molecules are to be named as 1-chloro-butane, and the second molecule is to be named as 2-chloro-butane. That is, when hydrocarbons undergoes free radical halogenation in the presence of sunlight, it gives the isomers, however, which are difficult to separate as a pure compounds. Consequently, the yield of any one compound is low. That is, the yield of any one isomer is very low. Next method of preparation of alkyl halides by using alkenes. Here, when alkenes are treated with the hydrogen halides, it gives two products. However, only one is the major product as per Markovnikov's rule. For example, let us take ethene. When ethene undergoes addition reaction in the presence of hydrogen halides, it gives, that is the replacement of double bonds, it gives hydrogen and another one is halogen. So it gives haloalkane. It is to be happen only in the case of symmetrical alkenes. In the case of unsymmetrical alkenes, that is CH3, CH double bond, CH2. So the reaction takes place according to Markovnikov's rule. That is, the negative part of the hydrogen halide attached to the carbon-carbon double bond containing less number of hydrogens. That is, the product is CH3, CH, and it is X, and single bond CH3, and another product is CH3, CH2, and CH2, X. However, so the first product is major product and second one is minor product, and it is minor product. For example, let us take CH3, CH double bond CH2 and reaction with the hydrogen halide. So it gives the product according to Markovnikov's rule. Negative part always attached to the double bonded carbon has less number of hydrogens, and another product, that is CH3, CH2, CH2I, that is 1, 2, 3, 2 iodo propane is the major product. It is the major product, and 1-iodopropane is minor product. Minor product. 2-iodopropane is the major product and 1-iodopropane is the minor product. Next one, that is the addition of halogens. When alkene undergoes halogenation, that is bromination, in the presence of CCl4, carbon tetrachloride, it gives vicinal dihalides, that is double bonds are replaced by the halogen. That is, vicinal means the halogen atoms attached to the adjacent carbon atoms. That compounds are generally to be called as vicinal dihalides. Since the discharge of reddish brown color of bromine is an important method for the detection of double bond in a molecule. That is, the double bonds present in a molecule are simply, it is to be called as unsaturation of the hydrocarbon. Unsaturation can be identified by treating it with the bromine, because this bromine has brown color. When it is treated with the unsaturated compounds, the brown color gets discharged. That indicates the presence of double bonds in a molecule. Next method, that is halogen exchange method. Halogen exchange method. That is, name itself indicates that there is an exchange of halogen by another halogen, in which there are two important methods. One is Finkelstein reaction, another one is Schwarz reaction. Let us see one by one. That is Finkelstein reaction. That is, Rx, alkyl halides, reacts with the sodium iodide, so there is a replacement of X by I, so it gives the product Ri plus NaX. This reaction is to be called as Finkelstein reaction. Here the halogen is either Cl or Br. Halogen is either Cl or Br. Let us take an example. First one, that is methyl chloride, CH3Cl. So when methyl chloride reacts with the sodium iodide, the Cl from the alkyl halide gets replaced by the iodine. So it gives the product CH3I plus NaCl. That is methyl chloride to be converted into methyl iodide. So these reactions are to be called as halogen exchange reactions. And next method, that is Schwarz reaction. When alkyl chlorides or bromides are treated with the metallic fluorides, so metallic fluorides such as AgF, silver fluoride, or Hg2F2, mercurous fluoride, or cobalt fluoride, COF2, or SbF3, antimony fluorides, SbF3. That is, when alkyl chlorides or bromides are treated with the metallic fluorides, the alkyl fluorides or fluoroalkanes are formed. Let us take an example, that is methyl bromide. That is, when the methyl bromide reacts with the silver fluorides, so there is an exchange of halogen, that is Br is replaced by the fluorine, so it gives CH3F plus AgBr. Or one more example, that is CH3Cl and reacts with the AgF, so it gives the product that is CH3F plus AgCl. That is, next, methods of preparation of haloarenes. That is, the two important methods to be used to prepare the haloarenes. First one, that is from aromatic hydrocarbons. It is also to be called as electrophilic substitution reaction. Very, very important for 2 marks. That is, when aryl chlorides or bromides can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalyst. That is, when toluene means benzene ring and one methyl group, so it is to be called as toluene. When toluene undergoes halogenation in the presence of Lewis acid, that is Fe acts as a Lewis acid in the dark medium, so it gives the electrophilic substitution product, electrophilic substituted product, that is CH3 and halogen attached at the ortho and para position. Halogen attached at ortho and para position, CH3, and it is X. So this product is to be called as ortho halo toluene, and it is to be called as para halo toluene. Ortho halo toluene and para halo toluene. Let us take an example, that is, when the toluene reacts with chlorine in the presence of iron as a catalyst, so it gives, that is, positive part attached at the ortho and para position. So at ortho, that is here, and the para position, that is CH3, and it is here. That is, in the first year already we learnt about the resonance structures of the toluene. In that case, there is an more electron density at ortho and para position. Hence, the electrophile Cl plus attached at the ortho and para position. So it does not produce meta position, because at the meta position there is an positive charge. Positive gets repelled with each other. Hence, the electrophile always attached only at the ortho and para position. So it is to be named as orthochlorotoluene, and it is to be called as para-chlorotoluene. The ortho and para isomers can be easily separated due to large difference in their melting points. That is, ortho product and para products can be easily separated due to the large difference in the melting points, and iodination is a reversible reaction. The product Hi is a good reducing agent which reduces the haloarenes back to hydrocarbons. Hence, the Hi formed during the reaction is removed by adding oxidizing agent like HNO3 and HiO3. That is, instead of chlorine, if we take iodine, the obtained product undergoes reversible reaction. Hence, the reaction takes place in the presence of strong oxidizing agents. And fluoro compounds are not prepared by this method because of the high reactivity of fluorine. That is, this method is the best method for the preparation of chloro or bromo substituted products. And the next method of preparation of haloarene, that is Sandmeyer's reaction. That is, When primary aromatic amines dissolved in a cold aqueous mineral acid, that is primary aromatic amine, that is primary aromatic amines means that is Ar and it is NH2. So this molecule is to be called as aniline. So when aniline is treated with the sodium nitrite, that is NaNO2, in the presence of hydrogen halide, and the reaction takes place at 273 to 278 Kelvin temperature. So it gives benzene diazonium salts. Benzene diazonium salt, that is the hydrogen atoms are gets N2X. It is N2 plus and it is X minus. And the obtained product on treating with the cuprous halides, CO2X2, cuprous halides. So it finally it gives the main product, that is C6H5, and it is X plus of N2 gas. Here X is either Cl or Br. So this benzene diazonium halides on reaction with the cuprous halides, it gives aryl halides.